Hello, dear students. We are continue our lessons. Today is laboratory work number 8. The theme of our laboratory work, research of the process of electrospark treatment details. The purpose of the work, a practical study of the process of electric spark machining of parts and the study of the influence of process parameters on its accuracy and productivity. Write down to your notes the theme of our laboratory work, the purpose of the work, and equipment, instruments, and accessories. Equipment, instrument, and accessories. It's an electro-erosive copying and broaching machine, electrode tool, preparation, vernier calipers with measurement limits of from 0 to 125 millimeters, and a reading value along the vernier of 0.1 millimeters. Chassis 125 0.1. Micrometer with a measuring range of 0.25 millimeters. MK 25 1. Instrumental microscope MMA. Stopwatch. Write down to your notes. Equipment, instruments, and accessories. Let's continue our laboratory work. So we start brief theoretical provisions. Among electrophysical methods, electrical discharge machining occupies a very important place. Using electrical erosion, it is possible to process conductive materials of any mechanical strength, rigidity, viscosity, fragility, obtain a predetermined roughness of the threaded surface, and process complex surfaces that cannot be obtained by cutting. Electrical discharge machining, EDM, involves changing the shape, size, roughness, and surface properties of a workpiece under the influence of electrical discharges as a result of the destruction of electrodes made of conductive materials when a pulsed or direct electric current is passed between them. The workpiece and tool are connected to a current source, a pulse generator, and placed in a dielectric liquid, like in figure 8.1. You can see the figure 8.1 scheme of electrical discharge dimensional processing. 1. It's electrode tool. 2. It's bus. 3. Workpiece electrode. 4. Dielectric liquid. And 5 is stable. And 5 is stable. In the pulse generator, capacitor C is included in the charging script, charged through resistor R from a direct current source with a voltage of 100-200 volt. When the voltage on electrodes 1 and 3 forming the discharge socket reaches the breakdown voltage between the microprotrusions on the electrode and the instrument EI and the workpiece electrode WE. An electric discharge occurs. The discharge energy, individual pulse, is determined by the formula 8.1. In this formula, you can see C, U. C, it's capacitor capacity, microfarad. U, DC supply voltage, discharge socket, volt. The power realized in the inter-electrode clearance depend on the frequency and energy of the pulses, watt. And the power is equal W multiplied by F. W, the energy of an individual pulse, joule, and small f, its pulse transmission frequency in impact per second. In this case, a thin conductive channel 4 is formed like in figure 8.2. On the figure 8.2, you can see the scheme of physical processes in the inter-electrode clearance during electrical discharge machining. A thin conductive channel 4 is formed, which closes the electrodes. A high density current pulse flows through the forming conductive channel. The discharge channel expands, and the temperature in the discharge zone reaches several thousands degrees. Section of electrodes 5 and 7 in the discharge zone, 5 electrode and 7 in the discharge zone, melt and evaporate. Under the influence of high temperatures, the liquid in the discharge zone decomposes, evaporates, and together with metal vapor forms a bubble that quickly expands into the surrounds liquid, where it solidifies in the form of tiny particles. Hard erosion products are removed from the interelectrode clearance under the influence of shock waves and fluid flow caused by an electrical discharge. Holes are formed on the surfaces of the electrodes where the discharge passes. The dimensions of the holes depend mainly on the energy and duration of the pulses and the electrical erosion resistance of the materials. In pauses between pulses, the working fluid restores its dielectric properties, deionizes. The next discharge will take place in the place where the distance between the tool and the workpiece is minimal. This creates a second hole line on the surface of the workpiece. When exposed to a series of electrical pulses, a layer of materials is removed from the surface on the workpiece. Continuity of the process is ensured by supplying EI. The constancy of the interelectrode clearance is ensured automatically using tracking systems. When performing electric spark processing, direct polarity is used. That is, the EI is connected to the cathode and the EC is connected to the anode. The pulse duration is from 20 to 200 microseconds. The size of the pulse energy is regulated by selecting the capacitance of the capacitors. As the capacitor capacity increases, the stored energy increases and consequently the process productivity increases. Depending on the amount of energy consumed per pulse, the processing mode is divided into hard and soft. The hard mode is characterized by increased productivity, reduced accuracy, and increased roughness of the machined surface. It is used for pre-processing. The soft processing mode allows obtaining dimensions with an accuracy of up to 0.002 millimeters with surface roughness RA 0.63, 0.16 microns. Electrical discharge machining can be carried out using a profiled or non-profiled tool electrode. In the first case, its dimensions and shape of the working surface are determined in accordance with the given shape of the surface of the workpiece. In the second case, the electrode tool has a simple shape, disc, rod, or wire, which is only partially related to the size and shape of the electrode part. Depending on the direction of supply of the electrode tool, different schemes of electrical discharge dimensional processing are used, like in figure 8.3. Schemes of electrical discharge dimensional processing. With the electrode tool has a simple shape, disc, rod, or wire. In this case, it is possible to obtain through and blind holes of any cross-sectional shape and holes with curved axis using a profiled electrode tool and cut workpieces from sheets using a wire electrode tool. This allows this method to be used for the manufacture of stamps, molds, cutting tools, various meshes, etc. For electrical discharge machining, special machines are used, both with and without CNC. The use of CNC machines makes it possible to produce parts of complex geometric shapes using simple electrodes. Please write down to your notes the figure number 8.2. So we are continue. In this case, it is possible to obtain through and blind holes of any cross-sectional shape and holes with curved axis using a profiled electrode tool, and cut workpieces from sheets using a wire electrode tool. This allows this method to be used for the manufacture of stamps, molds, cutting tools, various meshes, etc. For electrical discharge machining, special machines are used, both with and without CNC. The use of CNC machines makes it possible to produce parts of complex geometric shapes using simple electrodes. Of the electro-erosive machines, the most widely used in industry are coordinate broaching, copy cutting, and universal copy broaching machines. The electro-erosive copying and piercing machine has the following design, like in figure 8.4. Scheme of electro-erosive copying and piercing machine. A work table 2 is mounted on the frame 1, on which the workpiece is fixed. The treatment is carried out in bus 3 with working fluid. The electrode tool 18 is fixed in the electrode holder 8. And by means of carriage 5, 10, moves into mutually perpendicular directions in the horizontal plane. The electric tool oscillates and gradually moves towards the workpiece according to the signals from the controller, which drives the motor 6 and the vibrator 7. Mounted on the holder 4. The table and the electrode tool are isolated from the machine bed with dielectric spacers 17. The electrical part of the machine includes a pulse generator 9 and control 11 with devices for monitoring processing modes. The working fluid is supplied to the bus from tank 14 through line 12 using pump 15. Line 16 is used to drain the liquid into tank 14. When performing electrical discharge piercing operations on a machine, the electrode tool moves at a speed of pi alone in relation to the workpiece. In this case, the workpiece is monionless. This is how holes are pierced to a depth of up to 20 diameters using a rod EI. And up to 40 diameters when using a tubular EI with rotation of both the electrode and the pad and simultaneous pumping of the working fluid through the EI. The flashing speed reaches from 2 to 4 millimeters per minute. Process performance is in electrical discharge machining can be determined using formula 8.3. K multiplied by W multiplied by F. In this formula, K is a coefficient that takes into account the properties of the material being processed, the pulse duration, and the composition of the medium. In the table 8.1, you can see comparative machinability of materials and alloys. For example, if we using processed material is still 45, then relative metal shorting speed is equal 1. And for hard alloys, for example, VK10, the relative metal shorting speed will be equal from 0.3 to 0.32. During electrical erosion, preferential removal of material from one of the electrodes is observed, even if the electrode materials the same. Also, the cathode surface also experience partial erosion destruction with short pulse durations from 5 to 200 microseconds. Only a minimal fraction of ions manages to reach the cathode surface. Therefore, the cathode surface experiences significantly less erosion damage compared to the anode surface. That is why the workpiece is made as the anode and the tool as the cathode. This polarity is called straight. With longer pulse durations, many ions manage to reach the cathode surface and having more energy compared to the electron flow, cause intense erosion of the cathode. In this case, processing is carried out in reverse polarity. EI is the anode and EC is the cathode. The material of the electrode tool, depending on the serial production and processing features, can be copper, brass, aluminum, gray cast iron, carbon steel, tungsten, and special alloys. The most widely used materials are copper, brass, tungsten, and cast iron. The best wear results are shown by graphite materials that operate stably at both low and high frequencies. Tungsten electrodes occupy an intermediate position between graphite and copper. When processing carbon steel, tool steels and heat resistance nickel-based alloys, graphite and copper EIs are used. For raw EDM of workpieces made from these materials, EDM made from aluminum alloys and cast iron is used, and when processing holes, EDM made from brass and is used. When processing hard alloys and refractory materials based on tungsten, molybdenum, and number of other materials, EI from composite materials is widely used since using graphite. EI does not provide high productivity due to the low stability of the electroerosion process, and copper EIs have high wear reaching 10% and high costs. Electrical discharge machining is carried out in buses filled with a dielectric liquid, which cools the electrodes and the products of their destruction, localizes their emissions, and also reduces the magnitude of sides discharges between the electrodes, which increases the accuracy of machining the workpiece electrode. Industrial and transformer oil, kerosene, and processes water are used as working fluids. Depending on the properties of the working environment, the share of useful use of the pulse energy and its maximum powder change. Therefore, optimal dielectric media are used for each type of processing. Thus, in electroerosion process with low pulse energy, high productivity is ensured by distillated and industrial water and kerosene. In raw modes, heavy oil fractions, lubricants, diesel fuels, etc. are used in the electric pulse mode. The dimensional accuracy and roughness of the machine surface depend on the processing modes. Surfaces obtained by electrical discharge machining differ significantly in the nature of roughness from surfaces obtained by cutting. Micro-roughness have the form of holes regularly located on the threaded surface. The boundaries between individual inequalities are made correctly. After processing at raw condition, shiny surfaces are obtained in which spheroidal fused protrusions, which are welded disparate metal particles, are noticeable by reducing the pulse energy. Matte surfaces are obtained. The surface profile formed during the process of electrical discharge machining does not completely coincide with the initial shaping profile of the tool electrode due to machine errors, heating of the workpiece, vibrations, erosion processes, and tool wear. Like in figure 8.5. On the figure 8.5, you can see diagram of the formation of a lateral clearance between the electrode tool and the workpiece. you can see workpiece and work tool. The processing process occurs when there is a clearance C between the tool electrode and the workpiece being processed, and this must be taken into account when designing the tool. The change is surface micro-relief is mainly influenced by the electrical processing mode. The relationship between the height of micro-roughness H and the pulse energy W has the following form: 8.4. Height of micro-roughness H is equal C suffix M multiplied by W by pulse energy to the power of P, where C suffix M is a coefficient characterizing the material being processed, W pulse energy, R its exponent. For carbon steels and alloys, C suffix M is equal from 190 to 205, and R its exponent. Exponenta P, not R. 0.33 from 0.33 to 0.4. It's for carbon steel and alloys. And for hard alloys, C suffix M is equal 67 and P is equal from 0.36 to 0.4. The depth of the defective layer, thermal affected zone, also depends on the pulse energy. This depends for steel 45 with a hardness of 48 HRC is presented in table 8.2. Table 8.1 and table 8.2. Thermal effect of pulse energy on the surface of part during electrical discharge machining. However, fluctuations of the size of the inter-electrode clearance cannot be taken into account in advance. It has been established that the lower the machinability of the material, the greater the wear of the electrode. The sum of the various errors caused by EDM process gives the total process error. Write down to your notes the short theoretical sequences and work sequence. Familiarize yourself with the features of the electrical discharge machining process. Learn the structure and operation of an electric spark machine. After checking your readiness for work, receive an individual assignment from the teacher, including the following information: type and brand of processed material, type and grade of tool electrode material, list of processing modes. Place on the parts on the machine table and for each processing mode, calculate the power. For each processing mode, calculate the power P according to the formula 8.2. implemented in the microelectrode clearance the height of the micro-roughness of the processed surface. Formula 8.1, using the table of processing modes and processing productivity taking into account the processing time and the volume of removed metal. The volume of metal removed is calculated by the formula on your screen. D suffix E, diameter of electrode tool. B, pad thickness in millimeters. The productivity Q of electric spark machining is measured by the volume of metal removed from the surface of the pad per minute. It can be generally expressed by the following formula. You can see this formula on your screen. Q is equal V divided by T. V, it's a volume of metal removed. And T, the hole piercing time. Enter the result of measurements and calculations in the table 8.2. Write down to your notes the table 8.2 and the results of calculation. Write down to this table 2. Draw graphs of the dependence of tool wear, hole machining accuracy, and machining productivity on the discharge power. Create a report. So your report content. Scheme of electrical discharge piercing and the formation of a lateral clearance between the workpiece and the electrode tool. Table with initial process parameters. Table with experimental results. Graphs of the dependence of electrode wear, processing error, and processing productivity. And conclusions from the work. So please start your work. After some minutes, I'll give you initial process parameters. Dear students, on your screen, you can see the initial data for these laboratory works. Please use these initial data to calculate all parameters and then load the table from the report. So it's your initial data.